These are the lesson activities for section 2.1. We have a bunch of example matrices and a couple of scalars, and we are supposed to test each of these statements with the given matrices and scalars, and then mark the statement as true or false. I'm going to do these all by hand, but you are welcome to use technology as long as you've done enough to know how to do the arithmetic. So A plus B that's A, and B is, you just add component-wise. Corresponding components get added together. So 3 and -1 is 2. -6 and 1 is -5. -1 and 3 is 2. 2 and 4 is 6. So there's A plus B. Now we're going to do B plus A. There's B plus A. So what we're doing here is we're testing whether addition of matrices is commutative. Can you change the order? So -1 and 3 is 2, 1 and -6 is -5, 3 and -1 is 2, 4 and 2 is 6. You get the same answer. This is true. And it turns out to be generally true. Whenever you add two matrices, it is commutative. A plus B equals B plus A. Now we're going to test the same concept, commutativity, for multiplication. A times B and B times A. So A times B So remember, to multiply matrices, you multiply the row times the columns. I'm going to multiply row 1 times column 1, and that's going to go in row 1, column 1 of the answer matrix. And I picture taking the horizontal column, the 3, -6, pick it up off the paper, turn it 90 degrees, and lay it on top of the -1, 3. The numbers that line up, you multiply together, and then you add the two results. So I'm going to have -3 plus -18 is -21. All right, then I'm going to multiply row 1 times column 2. And that's going to go in row 1, column 2 of the answer. So row 1 times column 2, that's going to be 3 times 1 plus -6 times 4. 3 plus -24 is -21. Now I've multiplied this first row times every column in the second matrix, so I'm going to move to the next row and multiply that times each column of the second matrix. -1, 2 times -1, 3. You're going to have -1 times -1, which is 1, plus 2 times 3, 6. So 1 plus 6 is 7. And then second row, second column, goes in second row, second column of the answer. -1 times 1 plus 2 times 4. So that's -1 plus 8 is 7. So that's A times B. Now we're going to do B times A. I'll do it a little bit faster this time. So B times A so -3 plus -1 is -4. Row times column. Yep. And then first row, second column, I get 6 plus 2 is 8. Second row, first column, I get 9 minus 4 is 5. And then -18 plus 8 is -10. So A times B times A, not the same. So in general, matrix multiplication is not commutative. You do not always get the same results, A times B and B times A. So that's surprising. The commutativity of multiplication in the real numbers is very ingrained in us. So we're going to have to make a mental note to keep track of the order of multiplication when we're dealing with matrices. All right, so if commutativity doesn't hold, and that was a little surprising, we want to check some other properties, namely the distributive property, to start. So A times B plus C, does that equal A times B plus A times C? Okay, so A is 3, -6, -1, 2. Oops. And then I'm just going to add B plus C in my head here. B plus C is going to be -1 and -3 is -4. 1 and -5 is -4. 3 and 2 is 5. And 4 and 1 is 5. So that's, I'm doing just this piece right now. A times B plus C. This is A. This is B plus C. All right, so when I multiply these, 3 times -4 is -12. -12 plus -30 is -42. Then 3 times -4, this is the exact same result. I get -42. And then -1 times -4 is 4. 4 plus 10 is 14. And same result for the last entry. 4 plus 10 is 14. All right, that's A times B plus C. Now I'm going to do AB plus AC. So A times B we've done already. It's this matrix right up here. So AB plus AC is going to be, AB is -21, -21, 7, 7, plus A times C, I'm going to have to do, I'm just going to do this sort of in my head right here. A times C. So I'm going to get -9 plus -12 is -21. And then -15 plus -6 is -21. And then 3 plus 4 is 7. And 5 plus 2 is 7. So this is AC. I just did it in my head by looking at the matrices up here. When you add them together, you get -42, -42, 14, 14. Same thing we got up here. So the two sides of the equation are the same. So this one is true. So it looks like the distributive property does hold. Now I have another test that looks like the distributive property, except that the A is on the right of the parentheses. And I want to know, does B plus C times A equal AB plus AC? All right, so B plus C we know is -4, -4, 5, 5, because I did that just a minute ago right here. And then times A, which is 3, -1, -6, 2. So that comes out to -12 plus 4 is -8. 24 minus 8 is 16. And 15 minus 5 is 10. -30 plus 10 is -20. So that's the left-hand side of my equation. And then the AB plus AC I've already calculated. It's this matrix right here, AB plus AC. -42, -42, 14, 14. They are not the same. So this one is false, which maybe that's surprising because we thought the distributive property was going to hold. But what happened is that we changed the order of the multiplication, right? I did B plus C times A, which is different than A times B plus C. So that's another place where the order of the multiplication matters when you're distributing as well. Okay, so if the order of the multiplication matters, then if I want to do b plus c times a, then when I distribute my a, I can make sure the a stays on the right, and maybe this will work. Maybe this time I can make the distributive property hold. So b plus c times a, I know is this matrix right here, b plus c times a. I've calculated it already. And then BA times CA. Oh, sorry, BA plus CA. BA plus CA. Okay, so B times A, I think I have already calculated somewhere. Here's BA. I got the result here. -4, 8, 5, -10. And I have to add that to C times A, which I'm not sure I've multiplied C times A. Nope, I've only done A times C. So I'm going to have to multiply C times A. I'm going to have to do that out. So C is -3, -5, 2, 1. And A is 3, -6, -1, 2. Okay, I'm going to multiply these two matrices. So I have -9 minus, -9 plus 5 is -4. And then I have 18 minus 10 is 8. And then 6 minus 1 is 5. And -12 plus 2 is -10. Add these together and I get -8, 16, 10, -20, which is the same as I got up here. So this did hold. The distributive property does hold as long as you are conscious of the order of the multiplication. You can't change the order of the multiplication. Okay, K times AB. K is just a number, it's a scalar, it's 5. And A times B I've already done a couple times here. A times B is this matrix right here, A times B. -21, -21, 7, 7. So I'm going to do 5 times -21, -21, 7, 7. Okay, so 21 times 5 is 105. -105, -105. 7 times 5 is 35. All right, so that's K times AB. Now I'm going to do B times KA. So B is -1, 1, 3, 4. There's B. And then I'm going to multiply that times 5 times A, and A is 3, -6, -1, All right, this is 15, -5, -30, 10. And then I'm going to multiply those. All right, so I have -15 minus 5 is -20. Already getting a different result. That's not -105, so I know that this is false. I'll just quickly finish this. So I get 30 plus 10 is 40. And then 15 times 3 is 45. 45 minus 20 is 25. And then -90 plus 40 is -50. Those are not the same, so this is false. So this looks like the associative property, being able to change around the matrix, the parentheses, but you'll notice that we actually also changed the order of a multiplication. It was A times B, A on the left, B on the right, and this looks like I just moved the K into the parentheses, but I also changed the order. I put the B first and the A second. So that's why this is false. This is another case where I have changed the order of the multiplication. So we're going to do another example where we do the associative property, moving the scalar into a different spot in the order of the multiplication, but we don't change the order for the matrix. I thought I was going to do that. Maybe I do it later. Okay. A times B is -21, -21, 7, 7. Find that. A times C is right here. Also -21, -21, 7, 7. Okay, identity times a matrix. Does that always give you A? And is it the same thing as A times the identity? So we're going to test it out. The identity is 1, 0, 0, 1. In this case, A is 3, -6, -1, 2. When you just do the rules of multiplying matrices, first row times first column, you put that in the first row, first column of the result. You have 1 times 3 plus 0 times -1, which is 3. First row, second column, you have -6 plus 0, -6. Second row, first column, you have 0 times -1. I'm sorry, 0 plus -1. And then second row, second column, 0 plus 2. And that is A. Check. Okay, and then I want to make sure the same thing happens if you change the order. A, 3, -6, -1, 2, times the identity. This is not a given because, as we've established, matrix multiplication is not necessarily commutative. But we want to see if there's an exception for when you're using the identity matrix. So this comes out to 3 plus 0 is 3, 0 plus -6, -1 plus 0, and 0 plus 2. That is also A. So this is true. If you multiply the identity times a matrix or a matrix times the identity, you get the matrix back. So that is an exception where matrix multiplication is commutative if you're using the identity matrix. Okay, now we have this is a more complicated looking statement. It says, if AB equals AC, then it must be the case that B equals C. So I'm supposed to use the matrices that they gave me here. So I'm going to multiply AB and AC and make sure they're the same. Okay, so A times B, we've done before. Let's just go back and get that matrix. And A times C, I've also done before. So they are the same. So it is true, in this case, AB equals AC. Is it true that B equals C? Here's B, here's C. They are not the same matrix, so this is false. So this is also surprising. When you're dealing with the real numbers, if I gave you an equation that said AB equals AC, you could then conclude that B equals C for real numbers. Can't do it for matrices. All right, now we're going to look at another operation you can do with matrices called transposition. We're going to transpose a matrix, which means you make all the rows columns and columns rows. So I'm going to take A times B and transpose it. Here's AB right here. So I'm going to transpose it in one step. So instead of negative 21, negative 21 being the first row, it's going to become the first column. And instead of 7, 7 being the second row, it becomes the second column. So that's AB transposed. And then A transpose B transpose, that I'm going to have to do that multiplication out. So A transpose, looking at A right up here, I'm going to transpose it. So I get 3, negative 6, negative 1, 2, times B transpose, negative 1, 1, 3, 4. Multiply these together, and I get negative 3 minus 1 is negative 4. 9 minus 4 is 5. 6 plus 2 is 8. And negative 18 plus 8 is negative 10. These are not the same. False. So you can't take that transpose and apply it to each matrix in order. Here's a very similar looking example. AB transpose, I know what that is. AB transpose is negative 21, negative 21, 7, 7. Calculated that right over here. And then it says compare that to B transpose A transpose. Okay, so B transpose is negative 1, 1, 3, 4. A transpose was 3, negative 6, negative 1, 2. If I multiply these, I get negative 3 minus 18 is negative 21. 1 plus 6 is 7. 3 minus 24 is negative 21. And negative 1 plus 8 is 7. These are the same. So this is true. So when you're taking a transpose of a product, AB transpose is the same thing as B transpose times A transpose. So you can, as long as you change the order, you can do the transpose on the matrices separately. Okay, A plus B transpose, is that the same thing as A transpose plus B transpose? So A plus B is 2, negative 7. So I'm looking at A and B up here and just adding them in my head. So I did 3 and negative 1 is 2, negative 6 and 1 is negative 7, negative 1 and 3 is 2. So I'm going to have 2 and 2 plus 4 is 6. So 2, 6 is my last row. Then I have to transpose it. That's A plus B. Transposed is 2, negative 7, 2, 6. All right, A transpose plus B transpose. A transpose is negative 1, 1, 3. Nope, that's B. Hold on. Okay, A transpose is this matrix right here. 3, -6, -1, 2, plus B transpose, -1, 1, 3, 4. So that gives me 3 and -1 is 2, 2, -5, 6. Did I mess up before? Should be -5 above. A plus B, the lower left entries. Okay, I'm just checking A plus B here. So I should have 2, -5. Yep, I just added wrong. Okay, this is -5. So this is -5, and these are the same. So this is true. Okay, last one. If two matrices are multiplied together and you get 0, does it have to be the case that A is the 0 matrix or D is the 0 matrix? So A times D, I'm going to write out my A and my D. So A is 3, -1, -6, 2. D, to go up and look at that, D is 2, 4, 1, 2. Okay, so I multiply A and D. I'm expecting to get 0, the 0 matrix. So 3 times 2 is 6, -6 times 1 is -6, so 6 and -6 is 0. And then I get 12 minus 12, -2 plus 2, and -4 plus 4. Yes, so A times D is 0, but neither A nor D were 0. So this is false. Another surprising result. If we were talking real numbers and you multiply two real numbers together and get 0, it must be the case that either A is 0 or D is 0. One or the other would have to be 0. Not the case with matrices.